Welcome to today's paper reading. Today's paper is titled, If LLM is the Wizard Then Code is the Wand, a survey on how code empowers large language models to serve as intelligent agents. This paper was published on the AR14 preprint by Huang and colleagues from the University of Illinois Urbana-Champaign. The abstract highlights the integration of code into large language models, LLMs, which not only enhances their code generation capabilities but also significantly improves their reasoning abilities. This improvement allows LLMs to tackle more complex natural language tasks. The unique properties of code, such as logical consistency and modularity, enable LLMs to produce structured and precise intermediate steps, which can be connected to external execution through function calls. Additionally, the compilation and execution environment of code provides diverse feedback for model improvement. The abstract also discusses how these advancements have transformed LLMs into intelligent agents, IAs, capable of understanding instructions, decomposing goals, planning and executing actions, and refining from feedback, which are crucial for success in downstream tasks. Finally, the abstract outlines several key challenges and future directions for further empowering LLMs and IAs with code. The inclusion of code in the training data of large language models, LLMs, has become essential. Notable models such as Llama 2, GPT 3.5, and GPT-4 incorporate code into their training processes. This practice is not only beneficial for commercial applications like GitHub Copilot but also significantly enhances the model's reasoning abilities. As a result, LLMs are increasingly being used as primary decision-making hubs for intelligent agents, IAs, showcasing exponential growth in capabilities. This survey aims to elucidate the widespread adoption of code-specific training in LLMs and how it enhances these models to act as IAs. Unlike previous surveys that focus on either code generation abilities or listing IA tasks, this survey provides a comprehensive understanding of how code assists LLMs and where it benefits them as IAs. Figure 1 illustrates how code enhances large language models, LLMs, and their applications as intelligent agents, IAs. Traditional LLMs perform well in natural language tasks, but incorporating human interpretable and machine executable code significantly boosts their performance as IAs. This enhancement is likened to equipping wizards with mana-boosting wands, enabling intricate operational steps that improve decision-making, execution, and self-improvement capabilities. In this section, we define code as any formal language that is both machine executable and human interpretable. This includes human-readable programming languages but excludes low-level languages like machine language. Additionally, predefined formal languages, such as function sets in WebGPT, are included as they can be parsed and executed in a rule-based manner. For LLMs, code training follows the standard language modeling objective applied to code corpora. This approach leverages the sequential readability of code, similar to natural language. The training process involves optimizing the language modeling loss, which is calculated over a code corpus. There are two main training strategies: training a pre-trained natural language LLM with code, as seen in models like Codex, or training a LLM from scratch with a blend of natural language and code, as demonstrated by CodeLLM. When using other predefined formal languages for training, the process is referred to as code fine-tuning, which involves optimizing the LLM with a smaller dataset compared to natural language pre-training. Figure 2 provides an overview of the organization of the paper, highlighting a curated list of the most representative works discussed. The complete list of works is detailed in Appendix D, offering a comprehensive view of the research landscape covered in the paper. This figure serves as a roadmap, guiding readers through the structure and key contributions of the paper. Code pre-training significantly enhances the performance of large language models, LLMs. Firstly, it strengthens LLMs' programming skills, enabling them to master over 10 programming languages and achieve unprecedented success in solving complex coding problems. For instance, Codex, with 12 billion parameters, can solve 72.31% of challenging Python programming problems. Secondly, code pre-training empowers LLMs with complex reasoning capabilities, improving their chain of thought, COT, performance. This is evidenced by a remarkable accuracy increase from 15.6% to 46.9% in mathematical reasoning tasks. Lastly, pre-training on code enables LLMs to better capture structured knowledge, enhancing their performance in tasks requiring common-sense reasoning and visual understanding. This is demonstrated by models like Chaoqi and Code4Struct, which show improved few-shot and zero-shot performance in various reasoning tasks. Figure 3 illustrates the significant impact of code pre-training on the performance of large language models, LLMs. The figure highlights 3 key areas where pre-training on code has notably benefited LLMs, enhancing programming skills, empowering complex reasoning capabilities, and enabling the capture of structured common-sense knowledge. These enhancements are crucial for improving the overall effectiveness and versatility of LLMs in various downstream tasks and applications. Figure 4 illustrates the code-centric tool calling paradigm, which acts as a unified interface connecting large language models, LLMs, with a wide array of functional ends. This paradigm is crucial as it facilitates numerous tasks that span across different modalities and domains. By dynamically generating tokens that invoke execution modules with adaptable parameters, this approach enhances the flexibility and scalability of LLM applications. Importantly, it allows LLMs to engage with numerous functional ends, expanding both the quantity and variety of accessible tools and execution modules, thereby enabling them to handle more complicated tasks. The code-centric paradigm allows large language models, LLMs, to dynamically generate tokens that invoke execution modules with adaptable parameters. This approach enhances the flexibility and scalability of LLMs' interactions with other functional ends. These functional ends empower LLMs to access external knowledge, engage with diverse modalities, and interact effectively with various environments. Applications of this paradigm include enhancing text-based tools, extending tool learning to multimodal tools, and enabling LLMs to tackle tasks in the physical world, such as robotics and autonomous driving. Table 1 highlights the evolution of connecting large language models, LLMs, to various functional ends for performing complex tasks. Initially, tool calls were hard-coded within the LLM's inference mechanism, limiting flexibility and accessibility. The introduction of the code-centric paradigm, marked by, revolutionized this approach by enabling connections through programming languages or predefined functions. This method significantly enhances the scalability of LLMs, allowing them to interact with a wide array of tools and execution modules across different modalities and domains. The table categorizes representative works by the type of function ends they connect to, the connecting paradigm used, the learning method, and the objectives or problems they aim to solve. This shift towards a code-centric approach not only simplifies the interaction between LLMs and functional ends but also amplifies the flexibility and scalability of LLM's application in diverse tasks. Figure 5 illustrates how large language models, LLMs, can be integrated into a code execution environment to enhance their self-improvement capabilities. By being embedded in such an environment, LLMs can collect feedback that is not only automatic but also faithful and customizable. This feedback mechanism allows LLMs to refine their performance based on the results of executed code, ensuring that the feedback remains relevant and precise for the task at hand. This approach leverages the deterministic nature of code execution to provide LLMs with reliable feedback, thereby facilitating their continuous self-improvement. The integration of LLMs with a code execution environment allows for automated feedback that is both deterministic and resource efficient. This feedback can take several forms, including simple correctness indicators, detailed textual explanations, and reward functions derived from execution results. To enhance LLM performance, various methods are employed: selection-based approaches like majority voting, prompting-based methods that leverage in-context learning, and fine-tuning-based strategies that update the model parameters. These methods collectively aim to improve the LLM's ability to handle complex tasks and provide more accurate outputs. In this section, we explore how code-empowered large language models, LLMs, significantly enhance the capabilities of intelligent agents, IAs. Firstly, in decision-making, Code integration improves the IA's ability to perceive and understand the environment, translating observations into structured formats that enhance planning. This structured approach is crucial for tasks requiring precise execution steps. Secondly, during execution, the use of formalized action primitives allows for direct parsing and execution, streamlining the process and improving efficiency. Additionally, code LLMs aid in organizing memory, making it easier to manage and access information. Lastly, the self-improvement aspect is enhanced through automated feedback from the code execution environment, which facilitates early error correction and continuous learning, crucial for the agent's performance in complex tasks. Figure 6 showcases the operational pipeline of an LLM-based intelligent agent, highlighting the integration of code LLM capabilities across various phases. The agent employs code-based planning in Step 2, which involves breaking down complex tasks into manageable steps using modular and unambiguous code. In Step 3, the agent parses actions into formalized function-like primitives and creates tools, ensuring direct execution without additional grounding modules. Step 5 focuses on automated feedback collection, where the agent's decision center, the LLM, operates within a code execution environment to integrate various evaluation modules for self-improvement. Overall, steps 0 to 10 in the pipeline benefit from the code LLM's enhanced understanding of structured information and perception. The paper identifies several key challenges for future research. Firstly, there is a need for explicit experimental evidence linking code pre-training to the enhancement of large language models' reasoning abilities. While certain code properties are believed to contribute, their precise impact remains unclear. Secondly, despite improvements from code pre-training, foundational models still fall short of human-like reasoning. Exploring other textual data sources and new training modalities could enhance reasoning capabilities. Thirdly, applying a code-centric paradigm presents challenges, particularly in learning to correctly invoke functions for complex tasks in domains like chemistry and biology. Enhancing this capability is crucial for enabling models to perform expert-level tasks. The incorporation of code into large language models, LLMs, has shown significant benefits. Firstly, code training enhances the LLM's programming skills and reasoning capabilities. This training allows LLMs to generate highly formalized functions, enabling flexible connections across various modalities and domains. Additionally, LLMs can interact with evaluation modules integrated in the code execution environment for automated self-improvement. These enhancements directly benefit the downstream applications of LLMs as intelligent agents, IAs, manifesting in improved decision-making, execution, and self-improvement processes within the IA's workflows. Despite these advancements, several challenges remain, which serve as guiding factors for potential future research directions. Figure 7 illustrates the advantages of code over natural language through a comparison of pseudocode for an intelligent agent class and its corresponding docstring generated by ChatGPT. The code demonstrates greater structure, expressiveness, and logical coherence, highlighting its superiority in detailed command expression, specific step indication, and control signal transmission. Programming languages, in particular, offer unique features such as logical operands, loops, nesting, and class definitions, making them highly suitable for complex structures and interactions with powerful execution environments. These environments provide valuable feedback mechanisms, enhancing the refinement and reasoning capabilities of the code. Figure 8 presents the statistics from ArcSieve, highlighting a significant and growing trend in recent research focused on code-based large language models, LLMs, and LLM-based intelligent agents, IAs. The data indicates that the usage of code plays a crucial role in the success of these advanced models and systems. The graph showcases a notable increase in the number of papers related to these topics, reflecting the increasing importance of code in the development and application of LLMs and IAs. Figure 9 presents a comprehensive list of the papers included in our survey. This list is crucial as it provides a detailed overview of the research that has been analyzed. Notably, it excludes papers that were used for performance comparisons between code and natural language, instead concentrating on those that have effectively utilized code to enhance the capabilities of large language models and intelligent agents. This focus ensures that the survey is comprehensive and relevant to the specific enhancement of these models through code augmentation. Table 2 outlines the 3 primary features of code that enhance the capabilities of large language models, LLMs, and intelligent agents, IAs. These features are structured and expressive, machine executable, and explicit and unambiguous. Each feature is linked to specific functionalities that these models and agents perform, such as strengthening programming skills, enhancing complex reasoning, and improving decision-making. Further details on how these features contribute to the models and agents' abilities can be found in the introductory sections of the paper. Thank you for watching.